Solving the plane sphere ambiguity in top-down structure for motion. Moving a camera with a viewing direction perpendicular to the ground plane is a critical configuration for radial self-calibration, meaning that radial distortion parameters cannot be determined uniquely. This motion is, however, common in many applications such as photogrammetry to generate elevation maps or top-down animal behavior studies. Resulting videos are often processed using structure for motion, where no or insufficient calibration lead to severe doming effects in the reconstruction. An example can be seen in this figure, where no calibration leads to a severely domed reconstruction with multiple revolutions. In the case of inaccurate calibration, the doming is reduced, but the reconstruction remains unusable for many use cases. Only in the case of very accurate calibration, the reconstruction is completely planar and usable. The contributions of the paper are as follows. First, we propose a minimal solver for two views with their viewing direction orthogonal to a shared ground plane and rotations around this viewing direction. And secondly, we propose an optional regularizer to remove potential remaining curvature. The problem is formulated as follows. Given 2D image correspondences and a fundamental matrix, we can write the epipolar constraint at the top given some function g that undistorts image points using the 1D Fitzgibbon division model in projective space. An essential matrix can always be decomposed back into a rotation under translation, and we now use the a priori motion constraint of a rotation around the viewing direction to constrain the rotation and to define the set of possible solutions P. Given 4 point correspondences, the problem can then be rewritten as a polynomial eigenvalue problem and solved using its companion matrix. Due to numerical inaccuracies, some curvatures may remain in the final reconstruction. To mitigate this, we define a regularizer for the final bundle adjustment. By gathering the viewing direction of all cameras, we define a dominant direction using singular value decomposition, and then add a regularizer minimizing the angle between a viewing direction and this dominant direction. To use these methods in SFM, we first use the minimal solver across all pairs of images to find a consistent distortion across the full video. Afterwards, the conventional structure for motion pipeline is executed, and finally the optional regularizer can be used to remove remaining curvature. In the first experiment, random points are sampled using the defined motion constraint, and the estimation errors of the minimal solver are plotted. As can be seen in the figure, the estimation errors are low for the rotation, the translation, as well as the distortion. In the second experiment, the minimal solver and regularizer is tested on a real-world dataset. In black, you can see the 3D points of an uncalibrated reconstruction with severe doming artifacts. Underneath, you can see the results after using the minimal solver, and in the last row, the results after the final bundle adjustment using our regularizer. In conclusion, we proposed a minimal solver using a priori motion constraints to disambiguate radial parameter estimation in top-down videos and a regularizer to remove remaining curvature afterwards. Both methods can be easily incorporated into existing structure for motion pipelines. In the future, we want to explore other solver techniques like automatic solver, and we want to analyze how stable the minimal solver is against deviations of the proposed motion constraint.